name appeared on the roll, then it disappeared, then it appeared back again. We still haven't seen him. This class didn't move. We were always in this room, right? Okay. A couple of my classes did change rooms, so I didn't think this was one of them. All right. Whoa. Yeah, I did it right. Okay. I just botched something up. That means I've got to go back. Okay, Sarah's here. Okay. All right, I have to go through and find where we were. This has a memory to it, but I happen to hit a button and then it loses its memory. Okay. All right. Here we go. I think this is where we pick up this time. All right, let me think now. We did meet, not a full period, but a little bit last Thursday. And I think maybe I had everything done. I had the new syllabus out there because they changed some things, added some stuff. And I got the code for the WebAssign if you're interested in using it. It's completely up to you. If you had to buy it when you bought your book, might as well get your money's worth from it. It has good tutorial and stuff like this. I just don't like assigning homework exercises from it because let's just go to this. If it had this problem on there and said find the arc length of blah blah blah, well, here's the problem. Oh no, it isn't. Oh yeah, it is. Look out there. Yeah, find the arc length of that. Okay, and that's all they said. Find the length of the arc intercepted by blah. Okay? Now, once you do all the things that are required, then you could have this as an answer, or 16 pi over 3 as an answer, or this is an answer, or 17, approximately 17 inches. I think that actually is a better answer than this one. But guess what? WebAssign's only looking for one answer. And if you don't know which one they're looking for, it tells you you're wrong. Well, you're not wrong. You're absolutely okay. It's just that you don't have it in the form they're looking for, but there's no indication of what form that is. Or sometimes there's not. So that's why I don't like to make assignments for homework in it, because I find that students get frustrated with it. I've worked this several times. I keep getting the same answer. I look at it and say, well, you got it right. Well, they told me it was wrong. No, it's okay. They just were looking for it in a different form. And to me, there's no reason for that kind of frustration. Okay? So that's why I use it. There's great tools out there, great problems and other things, and they talk you through it. And there's lots of good things about it, but I don't want you to introduce you to the frustration of it. So you decide. Use what you want of it. And it has really good tutorials. Okay. All right. Any questions before we move on?
I have a question about the homework from last
Yeah.
time. I don't know how to change it to like DMS form and change it back to degree.
Okay. Yeah, that was the one we didn't do any thing like that. So I'm glad you're asking. So you want to do a couple of those? Okay. And that was along about 47, 48, 49, and 50? Okay. So let's go back and let's do it here. You pick one of those or any one that you want. Okay, you want to do both of them? Okay. So this is page 268, and this is 4.1 exercises. and number 47. Is that right? Yeah, 47. A. All right. In these exercises, convert each angle measure to decimal degree form. Okay? So you're starting with 54 degrees and 45 minutes. Okay. Now it's asking for a decimal degree form. Okay. Now, first thing to note is, of course, 45 minutes, is that more than or less than a degree? Less, of course, yeah. What is 1 degree in minutes? Second? 1 degree in minutes. Of course, 1 hour in minutes. 60 minutes. Same thing here. Okay. So it's 60. Okay. So in decimal form, I already know the first part of that decimal. It's going to be 54 point something degrees. That's what it's going to look like. I just got to figure out the something. Okay, and you get it in decimal form, and I basically almost gave it away now. So let's just take the 45 minutes, and let's do our multiplication like we talked about before, and let's set that to degrees, understanding it's going to be a decimal form. Okay? Now, all right, the 2 blanks. This blank is for numbers. This is for units. Always put the units into place. What unit is going to go where? You're dealing with either minutes or degrees. One's going to go upstairs, one's going to go downstairs. Where it's going to go where? Okay, degrees will go upstairs, and minutes will go downstairs. Now you match numbers with degrees. And the question I just asked is, how many degrees in a minute, or how many minutes in a degree? Second? Okay, 1 degree is 60 minutes. You're absolutely right. 1 degree is 60 minutes. Okay? Now you can cancel out the minutes, and 45 divided by 60. Well, first, is there any common factor there? 15. 15 will go into 45 how many times? 3. 15 will go into 60 how many times? 4. So that's 3/4 of a degree. And written as a decimal form, that would be what? 0.75 degrees. So that's what goes here. 54.75 degrees. Okay? Make sense?
No, I think I can do that.
What's that?
I think I can do that.
Okay. All right. How about going the other way? Or okay, do you want to, okay. Let's look at 48 where they got seconds in there as well. You want to do A or B? Pick one. A, okay. So let's do 48A. Okay. 135 degrees, 10 minutes, and 36 seconds. Okay? Now, I gave you one way to do it. There is another way, but I don't know. How would you like to do this? And you were trying to get this into degrees and decimal forms, since you know that all this over here is less than 1 degree, and this is less than 1 minute. Yeah, it's all going to be a decimal. So, where do you want to start? Similar. Only difference is you got 2-step there, yeah. So what might we do first? Yes, let's do the seconds to minutes. So let's start with 36 seconds. You don't have to do it this way, but this is one way. 36 seconds, we're going to multiply that by a conversion factor to try to get it to minutes first. Okay? And then what do you do first? Minutes on the top, seconds on the bottom. 1 minute is 60 seconds. Okay, then the seconds cancel out, which is good. And what does that leave you with? What will go into what? Okay. Did I hear a 6? Yeah, 6 will go into 36. 6 times, and 6 will go into 60. 10 times. Now, since we're going to decimals, I'm not going to reduce that any further. I'm going to write this as 0.6 minutes. Is that okay? Because 6/10 is 0.6, right? Now, I'm going to add that to 10 minutes. So now we have 10.6 minutes. And now we want to get that to degrees, right? And just like before, we put minutes on the bottom, degrees on top. 1 degree is 60 minutes. Cancel out the minutes. And if you wanted to, you could divide out at least a 2, and that would be 5.3. You don't have to do that if you don't do it, and that would be a 30. And that's about all I can do that I can think of right now. So if you got your calculator, do 5.3 divided by 30. This one doesn't have the answer in the back, so we can't check it, but I think I'm fairly confident we're doing it right. Second?
1.7 and 6 repeating.
Okay. 1.7, is that what you said?
Or point.
Huh?
0.17.
Oh, 0.1. Yeah, of course it would be. Okay. I can't hear well. Okay. 0.17 with the 7's repeating or the 17 repeating?
The 6 is repeating. It's like 0.17.
0.171717 or 0.17777?
It's like 0.766666.
Oh, 666. Okay. Okay. 0.1766666 with 6 repeating. Okay, got it. Okay, I'm going to round that to 0.18, I think. And so you add that to 135, so it'd be 135.18 degrees. Okay. Okay. I don't see any reason to haul around a lot of extra decimal points. Okay. And you're okay going the other way. If you're given the fractional form, how do you get it in degree, minutes, seconds? Or is that what you originally asked?
I think I get it.
Okay. You just start and do the other way. You do 6/10 of a degree is 6 over 60 minutes. And then you make it pretty easy to go from there. I'm sorry, I didn't say that. 6 over 100 minutes. 6/10 is 6 over 6 over 10. What am I saying? 6 over 10 minutes, and then wait, 6 over 10 degrees, and then let me go on and show you how to do it. Just talking through it is not making a lot of sense. So let me clear that and start over here. Whoa, where did that come from? Okay. All right. 240.6 degrees. 240.6 degrees. Okay. Now, here's how I would do it. This is one way, it's not the only way. 0.6 degrees is the same as 6 over 10 degrees. Okay, right? Okay, and that's equal to, or yeah, let's go on and do it the same way we did before. Why not? Okay. Multiply that by blank blank. Let's go on and reduce that. Make it 3/5. Okay. I should have done that. Okay. 3/5. And you'll put degrees down here, minutes up here, equal blank minutes. Okay. Because that's what you want. Get it degree, minutes, seconds. Okay. And how many minutes in a degree or degrees in a minute? Yeah, 60 minutes is 1 degree. And then 5 will go into 60, 12, 36. So there's your 36 minutes. So it's 240 degrees, 36 minutes. Okay. Now, some of them may not come out quite that nicely, especially the 0.12 probably wouldn't. 0.58 probably wouldn't. There you'd have to go into seconds as well. Whoa, I put seconds down there, didn't I? You let me get away with that. Shame on you. That's minutes, not seconds. Okay. All right. Good deal. So that answers it. Okay. Let me get away from it before I mess something else up. Okay. Any other questions? Good question, by the way. All right. No more questions, then let's go to this one. All right. The formula for the length of a circular arc can help you analyze motion of a particle moving at a constant speed along a circular path. Blah, 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 right? So let's look at this. Consider the particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in the time t, then the linear speed v will be arc length divided by time. Centimeters per second, meters per second, miles per hour, whatever it is. That's your linear speed. How far you went in arc length divided by time. Now, moreover, if theta is the angle, remember, always in radian measure, because that arc length formula depends on you being in radian measure, so don't ever do it in degrees. If that theta is the angle regular in radian measure corresponding to that arc length s that it traveled, then the angular speed, and its symbol is this little symbol here. Does anyone know what that is? Looks kind of like a W, but too curvy, right? It's an omega. This is a Greek symbol for theta. This is lowercase theta. This is lowercase omega. Capital omega looks like a horseshoe, okay? But lowercase omega, and Greek alphabet has uppercase and lowercase just like we do. And some of the times the letters don't look. Our T's look like our T's, but our capital A really doesn't look like our little a too much. So just like here, capital omega is like this, little omega is like that. Lowercase Greek letter omega. The particle would then be the angular speed would be radians per second. So it would be the angle in radians divided by the time in seconds. So they give you these, but then they sort of leave it hanging, and they want you to figure out the rest of it. So that's what the next example or two will do. No, they won't. They skipped the next two examples. So let's go back and do those. Okay. All right, the first of these is a clock dial, okay? Here's our clock dial. I don't draw circles very well, okay? Where this is 12 o'clock, this is 3 o'clock, this is 6 o'clock, this is 9 o'clock, 1 and 2, 4 and 5, whoops, 7 and 8, 10 and 11. Okay, not very pretty, is it? Okay. Now, the second hand on the clock is 10.2 centimeters long. So here's the center of that clock dial, and here's the second hand, and the length of this is 10.2 centimeters. Okay, that's about between 4 and 5 inches, okay? It's shown in their picture, which is maybe just a tad prettier than mine, but not much, okay? Find the linear speed of the tip of the second hand as it passes around the clock space. Cheer class?
Yes.
Okay, what's your name?
Jared.
Second?
Jared.
Derek?
Jared.
Jared Woods?
White.
What?
White.
What? Right.
Yeah.
Okay, yeah. You're the one I kept seeing your name show up and then disappear, show up and disappear. So Jared Wright, okay. W-R-I-G-H-T.
W-H-I-T.
Second. Oh, White.
Yeah.
Okay, I'm sorry, I can't hear well. W-H-I-T-E. Okay. Jared. And that's what you go by, Jared?
Yep.
Okay. So this is your first day in the class. All right, good deal. Welcome. So let me take a quick time out here and go back over the course a little bit. Okay? Now we met, this is our fourth meeting. We missed most of last week. We came in for just a little bit on Thursday. So to catch up anything that you may have missed, I record everything. In fact, I'm recording this right now. This is what this is indicating. On a package called Screencast-O-Matic. And as soon as the class is over, then I upload that to Blackboard. Now, to YouTube. It takes a while for that to happen, so it won't be immediate. Sometime this afternoon, it'll be on YouTube. So let me start over with the course, and probably the best place to start is Blackboard. Are you familiar with Blackboard? Okay, good. All right, when you get to this class's Blackboard page, okay, it's the home page for this course. There will be a series of tabs in the upper left corner. Now, I only see the instructor side. I don't see the student side. And the instructor side, these are blue. I don't know if they are on yours or not. And like the second or third one, it's going to say content. If you click on that content tab, you're going to see a whole list of things show up. The very first thing in that list, hopefully, will be the syllabus. Okay? Now, you can read through the syllabus. You can, go through, follow everything in it, and that's fine. The last page of the syllabus is an acknowledgement page. Once you've read through the syllabus, ask me any questions if you have any questions about it, and you've gotten all your queries taken care of, then if you'll just sign that page or type in your name and email it to me or whatever, just to let me know you've acknowledged that. Okay, the second thing out there is the research paper instructions. There is a research paper due by the end of the term. I suggest you get it done earlier rather than later. But anyway, that's due by the end of the term. The instructions for that are there. Okay? Third thing is my locator card showing when I'm on campus, when I'm off campus, when I'm in class, when I'm out of class, when I've got office hours, when I'm on Birmingham campus, when I'm on Bessemer campus. Okay? All that's out there. Okay? On my locator card. Then you'll find all the PowerPoints that we'll possibly do. We may not get them all done, but all the ones we possibly. Chapters 4, 5, and 6 from the text. Every section has its own PowerPoint. So they're all listed there. The next things are some websites that either students have given me or that I found that I thought might be useful. Just give a different perspective looking at the same thing differently. Okay? So those are out there. And then the last thing listed, I think, is MTH113 YouTube videos. You go and click on that, then you'll see all the videos you'll see a whole bunch of videos. Okay. Now, the ones you'll see at the top of that will be ones that from the last time I taught the course. Okay? It goes by sections and stuff like that. To get to the ones we've done now, go all the way to the bottom of that, scroll to the bottom of the list, and the first one you see there, it says syllabus. That was the first day of class. The next day may have said, safety or something like that. And then the next one, all the ones after syllabus will be the ones from this term. The ones above will be from previous terms. The reason I don't wipe them all out at the beginning is that sometimes the system goes down. And I may just have to write on the board and not record things. Well, I'll leave the things out there I've recorded before, so in case we do miss a day, it'll still be there in some type of a form. Same book, same me, same everything. So it may not start and end at the same places, but it will be pretty close. So I'll leave them there until we do it this time around, then I take them off. Okay? So you'll see the top part will start losing and the bottom part will start growing. Okay? So that way you can pick up anything you may have missed. All right. Research paper, if you can, figure out what you kind of like to write that on a piece of paper. You'll hear me talk. Okay. On that first day of class, when I went over the syllabus, boy, did I go glory to tell. Now, actually, the syllabus that I was talking about there, and you'll see on the screen, is not exactly the same one that's out on Blackboard now, because the dean changed the syllabus on us after the term started and said you have to add these things. But the bulk of it's the same. The math part is the same. It's just the other stuff is different. And same thing with the locator card, probably the first day of class. I thought I was teaching a physical science class that got canceled. So, in fact, this class we thought might be canceled, but then we had some people that had to have it, so we stayed with it. Okay? Any questions? All right, so you can catch up where we are. Right now, notice you probably don't have a book. We're in the first section of chapter 4, 4.1. We're doing example 6, top of page 265. It's a clock face. And what I was just saying was the second end of the clock is 10.2 centimeters long. Okay? Showing it right. Find the linear speed of the tip of that second hand as it passes around the clock space. So what we're looking for is the linear speed as it's going this way, and that's usually given the symbol v, velocity, speed. Okay? How do we find that? What is linear speed or velocity? Distance traveled. Huh? There. Okay, arc length over time. Exactly. The distance traveled, which for that hand will be an arc length, divided by time. Okay? So how far is this going to go? Well, let's just pick a point, this point right here, and let's just let it go all the way back to here again. Okay? How far would that have gone? Say again? It doesn't matter where you start. You could have started at 12 and gone all the way around to there. I just started here, all the way around to there. It's the same distance. As you get one circle around, what is that distance you travel? Say again? That is the angle you travel. Exactly. What is the distance or the arc length that it cut? What was that formula? It's on the previous page, top of the page. Say again? Okay, wait. Okay, go to the top of that page. What is the arc length? S is equal to? Ah, okay. There it is, right there. I had it hidden from me. S equal R theta. Okay? Now, what's your R? On this problem, not that one. 10.2 centimeters. So the arc length, S, is equal to 10.2 centimeters. And what did you say the angle theta was? Yes, very good. What does that angle always have to be expressed in? Radians. Don't say 360 degrees. The formula doesn't work for degrees. It only works for radians. So what will this be? 20.4 pi centimeters. That's how far the end of the thing traveled. Now the big question, this is the formula you are going to, the linear speed, V, is equal to arc length over time. So we got the arc length, 20.4 pi centimeters. How much time did it take to go around there? Was anyone clocking it? Say again? Not minutes. This is the what hand? Second hand. 60 seconds. That's how long it takes to go around. So we know the time, don't we? Divided by 60 seconds. I can't write at all. Okay, pretty ugly, huh? Let me see if I can clean that up just a little bit. Oh, yuck, that didn't clean up at all, did it? Ooh, too much cleaned up. Okay, 60 seconds. All right. Now, if you wanted to, you could divide a few things out, but you got calculators, so just go on and plug them in. 20.4 times pi divided by 60. You got an answer? 1.0 what? Okay. They round to 1.07, okay? Centimeters per second. All right. Good deal. And in fact, this sort of makes good sense here. You think about pi is just a little bit more than 3, right? 3.14 times 20, that's just a little bit more than 60. So 60, a little bit more than 60 divided by 60 is going to be just a little bit more. So that's very reasonable. Good deal. All right. There is a checkpoint there. And by the way, since you weren't here to hear me talk about it before, every example they give in the book, this text, this author does the best job of providing auxiliary information, auxiliary sources for you of any author I've ever used. I don't like the publishers, but I like the author. At the end of every example, there's a checkpoint. And then right by the checkpoint, it says the audio-video solutions are available at larsonprecalculus.com, a free website. Absolutely free. So if you can't figure out how to do the checkpoint, go to larsonprecalculus.com. Every example has one. Later, you'll see that the homework exercises, and I always assign the odd numbers for 2 reasons. Number one, the answers to the odds are in the back. Okay? So you can check your answer, see if you got it right. If you didn't, and you can't figure out what you make you miss it, notice at the top of every exercise set, it says, see calcchat.com for tutorial help and worked out solutions for the odd number exercises. So if you can't get it figured out just from the answer in the back, then go to calcchat.com. And then something new they've added in this edition, occasionally they'll give you a red letter example number, and those are worked out at calcview.com. They don't list it here, but it's at the front of the book, calcview.com. Okay? Now, another thing, if you have a phone and can read this code here, it's like a barcode, it's only a 2-dimensional barcode, and can read that, you can go straight to it because you see every one of these that has a red letter one has that barcode by it. And you can get to the calcview.com that way if your phone can do that. Mine might, but I don't know it well enough to figure out how to do that, so whatever. Okay. So that was example 6. Let's move on to example 7. Okay. Any questions on 6 before I delete it? Okay. Well then, erasing 6, here is 7. Okay. The blades of a wind turbine, and I'll try to draw a wind turbine here. There's the thing, the pole that it sits on, and the blades are up here like that. Okay? And these blades are 116 feet long. Now, mine don't look like they're even, but they're supposed to be. So let's just say any one of these is 116 feet long. Okay? The propeller rotates at 15 revolutions per minute. The rotation here is 15 RPMs, and that stands for 15 revolutions per minute. Okay? What's that?
Just trying to finish.
Think what?
I was trying to remember what it meant.
Yeah, RPMs is revolutions per minute. Okay? All right, that's what they give us. This is planted here on the ground. And by the way, I don't know if y'all have seen these. My wife had professional meetings in near Salt Lake City this summer. It was the week between summer and spring and fall, I believe it was, or at the front end. I think that's when it was. So since I was off then, I got to go with her, and so while she was working, I got to tour around, just have fun. And what we did, we went up early so we could go because we really love Jackson Hole and Tetons. Jackson Hole and Tetons and Yellowstone. So we went up early to spend the weekend there and then drove over to Salt Lake City for her meetings. Okay? And we decided to take sort of a scenic route. Actually, we flew into Salt Lake City, then drove those other places and came back. So we made a sort of a tour, a loop of it, and there were some places in Wyoming and Montana that big fields, and they were cutting hay and doing other things, but in the fields were these wind turbines. I mean, plenty of room underneath where the farmers could do whatever they're doing, hay or whatever they're doing, cutting grain, whatever, but the wind turbines up there making electricity. It was in huge farms of these, you know. The wind on the plains go blowing, you know, just all the time. The other things were generating a fair amount of electricity at the same time, and absolutely no pollution. Oh, it was nice. Okay. All right. Never mind. Anyway, we've seen those. They're really impressive. Okay. The A part here says, find the angular speed of the propeller in radians per minute. So what we're looking for is our omega, angular speed, in radians per minute. Well, what's the closest thing we have to radians per minute given in the problem? We're given revolutions per minute. Okay? Now, we're at 15 revolutions per minute. What does a revolution mean? From one place, one time around, right? So if you have 15 revolutions per minute, then if we can relate that to radians, so let's do that. How many radians are there in a revolution? 2 pi. So this will be 15 revolutions. This isn't, it leads to this, it's not the same. 15 revolutions per minute times 2 pi radians per revolution, right? And that gives you 30 pi radians per minute. Now remember, we've said before, a radian really isn't a unit. We treat it like it's a unit, it's a ratio, but that's exactly what your omega is, 30 pi radians per minute. Because you got 2 pi radians for every revolution, and you have 15 revolutions per minute, so that gives you 30 pi radians per minute. So there's the A part. Pretty straightforward. Okay? All right. Now they did it slightly differently, but it still works the same way. So let's do the B part. And the B part here says, find the linear speed of the tip of the blade. So how fast is this going? Now it doesn't tell us what direction it's turning. Looking at this, I can't tell. Let's just say it's going clockwise. It may not be, but whatever direction it's going. So what is the linear speed there? Well, if S is equal to R theta, huh? Yes, it's r theta. Okay, so it's this thing. The linear speed v is equal to s over t, which would be r theta over t. Right. Okay? We know the r, but we know what theta over t is, don't we? Theta over t is this omega. Right? If you go back and look from the previous slide, let me go to it. Sorry, it's going to mess up a little bit here. Angular speed omega is equal to theta over t, and the linear speed is s over t, which is, and s is r theta over t, so this is merely r omega. We just figured out what omega was. We know the radius, so we have 116 feet times 30 pi radians per minute. Okay? Goodness gracious, this pen is doing strange things. Okay. Now, remember, radians is not really a unit, it's just a ratio. So there's really nothing there. This is going to give us the linear speed in feet per minute. So if you have a calculator, punch it in. 116 feet times 30 times pi. Okay, 10,000, second. Okay. You did 116 times 30 times pi. You may have said it, maybe I just can't hear well. 10,000, okay. 10,933 approximately feet per minute. Okay. Now, I'm not sure we can justify that many digits, but that is the answer they give. In other words, it's going pretty fast. I'm glad that blade is well off the ground, so if I'm on my tractor underneath it, I don't get a haircut at that kind of speed. Okay. All right. 10,933 feet per minute. Those things are moving. All right. And again, there's a checkpoint. So go for it. Any questions? All right. Let's move on to this, the sector of a circle. Okay? Sector of a circle is defined as a region bounded by two radii of the circle. Now, two radii of a circle, of course, are going to have the same initial point, which is the center of the circle. So if there's a radius and there's a radius, and the sector is the area, is the region bounded by the two radii and their intercepted arc. There's the theta. Guess what that theta is measured in? Radians always, don't ever do it in degrees. The formula won't work. Okay, now, how are we going to come up with a formula for that? Now, this is probably not an exact way to do it, but it's not too far off. Let's think about this. This length here, what is that length along the circle there? What do we call that? Arc length. And the symbol for that was S, remember? Okay. Now, this kinda, a little bit, sorta, looks like a triangle, doesn't it? Okay. And say the area of the triangle would be 1/2 base times the height, wouldn't it? Okay? Now, I'm going to cheat a little bit here. The base of course, I think is going to be the R, 1/2 the R. And the height, this isn't really the height, but let's just do it. Let's call that the arc length. And the arc length is R theta, right? right? So that would be 1/2 r squared theta, okay? Now that's a real dirty way to think of it, but it's a way that helps me remember it, okay? And that is, let's erase my scratch here, because all they do is just give it to you. And they say, well, for a circle of radius r, the area A of a sector with a central angle theta is 1/2 r squared theta. Okay? Blah. They just give it to you. I like to sort of have some sort of visual because I don't like memorizing anything. And so that gives it to you. Now, things to notice here, remember, the 1/2 is dimensionless, has no dimensions. The r has dimension length. It could be centimeters, miles, feet, yards, whatever. So that would be yards squared. Theta, measured in radians, is a dimensionless quantity. So, therefore, this is in square units, square feet, square miles, square centimeters, which is, of course, what an area is. So, just to keep in mind, if you keep in mind what the units are, yeah, the formula matches that. Okay? So 1/2 r squared theta. Whoa! They don't do the next exercise example either. Example 8. Let's calculate that. A sprinkler on a golf course, fairway, sprays water over a distance of 70 feet. Okay? So here's the head of the sprinkler, and it goes for 70 feet here, and it cuts an arc here to this other 70 feet. Okay? Because those are the radii, okay, of that sector. Okay? Through an angle of 120 degrees. I don't know if I'm close to 120 degrees, but let's just imagine I am. There's your angle theta. Okay? Rotates through an angle of 120 feet. Find the area of the fairway watered by that sprinkler. In other words, what is the area in here? Anyone remember what the area formula is? Can't look at the page. Okay. It's right there. Okay. 1/2 r squared theta. Okay. So I know what 1/2 is. It's 1/2. Now r squared. What is our r? 70, and 70 squared would be 4,900. That would be square feet. I'll put the units in there. And what's our theta? 120 degrees. Is that right? Oh, no, you can't use degrees. You have to use radians. So before you can use this formula, we got to go back here and do some head scratching and convert our 120 degrees times blank blank equal blank radians. Now, this is something we did before. You know what it is? Okay. Say that again. 2 pi over 3? It's 2 pi over 360. Okay. Right? Okay. Let's do the units. Okay. You haven't seen me do this. They have. I put a blank blank here. The first blank is for your numbers. This is a conversion factor. First blank is for numbers. Second blank is for units. Always put the units into place. Now, what unit is going to go where? One's above the line, one's below the line. The two units we're dealing with is radians and degrees. So what goes above, what goes below? Radians on top, degrees on the bottom. Why? So you can cancel out degrees and leave you in radians, right? Now, you match the numbers with the units, okay? Now, if you're talking about a circle, which this would have been a circle, okay, if it had gone all the way around, okay, And when you said 2 pi, that's how many radians around that circle, right? How many degrees would that have been? All the way around the circle. Second? 360. That's why it's 2 pi over 360. Okay? So it would be, but we can reduce that to be pi over 180. Because if you went all the way around the circle, if you go halfway, that's pi radians, and that's 180 degrees. So that's a little bit simpler ratio. Okay? So now we can reduce 120 over 80. Easy thing to do is wipe out the zeros at the end. Anything going to 12 and 18? Second? 6. 6 will go into 12. 2, 6 will go into 18. 3 times, so that'd be 2 pi over 3 radians. So 2/3 pi radian. That's what we put down here, not 180 degrees. Two pi over 3. And you don't have to put radians because that really isn't a unit. We treat it like it's a unit, but it really isn't. It's just a ratio. It's a dimensionless quantity. So now we can cancel out or divide away our 2's. And unfortunately, 3 won't go into 490, so it's just 4,900 pi times pi divided by 3. And what does that give you? Anyone do it? 4,900 times pi divided by 3. Okay, a little bit louder. And 31, is that what you said? Okay, we'll leave it that, round it to that, and that will be square feet. Okay? And again, that's a really good thing because pi is just a little bit more than 3. So the ratio of pi to 3 would be just a little bit more than 1. Something slightly more than 1 times 4,900 will be slightly more than 4,900. 5139, that looks like a very reasonable number. Good deal. Okay? Excellent. All right, there is another checkpoint. So be sure, and what I've recommended before, I don't remember if I said it in this class or not said it in the other. If some of these are a little fuzzy to you and you're not quite following, or you think, oh, I think I see it now, but, well, time out. Let me back off. I hear people say this usually around first test time. Oh, I follow what you're saying in class, and, I think I got it, but then when I get home and work on homework exercises or when it comes to test, I can't remember how we did it. So here's my antidote to that. Okay, this is, I think, will help cure it. As soon as you can. Now, if you don't have a class right after this one, you don't have to go eat right after this, go somewhere and try to do as many of these checkpoints as you can while it's fresh on your brain. That way, it's not just something passive you've seen me do, it's something active you've just done. Okay? So that's the best antidote to forgetting after class how you did it. And then sometime later do the homework exercises. Okay? You can do those right after class. That's actually the best time to do those too, but especially those checkpoints. And if you get stuck on them, there you have LarsonPrecalculus.com you can go to. And the homework exercise you can do CalCheck or CalcView.com. But we did finish the section. Let's look at the vocabulary at the beginning of the exercises. Two angles that have the same initial side and terminal side are blank. Coterminal, exactly, same terminals, okay? You assume they all start at the same initial. Number 2, one blank is the measure of the central angle that intercepts an arc equal to the radius of that circle. One is the measure of an angle, the central angle, so the arc is the same as the radius. That measures what kind of angle measurement. We only have 2 ways to measure angles. it's not a degree. Radian, all right, good. That is the definition of a radian. When the arc length is equal to the radius, you have an angle of 1 radian. Okay? Feel like a dentist here, pulling teeth. Okay. Number 3. 2 positive angles that have a sum of pi halves are called complementary angles, and 2 positive angles that have a sum of pi are called supplementary angles. Very good. Number 4. The angle measure that is equivalent to the rotation of 1/360th of a complete revolution about an angle's vertex is 1 degree. Perfect. Number 5. The blank speed of a particle is the ratio of the arc length traveled to the elapsed time. That's a linear speed, and the blank speed of a particle is the ratio of the change of the central angle with elapsed time. Second, angular speed, exactly. Linear speed, usually v. Angular speed, usually omega. Linear speed, some length unit, like centimeters per second. Angular speed, though, radians per second. All right. Number 6. The area A of a sector of a circle with radius r and central angle theta, where theta is measured in radians, is given by the formula. You can't imagine that, can you? There it is, 1/2 r squared theta. Very good. Okay, homework exercises. Do either 7 or 9, or both. And by the way, all the odd number exercises, the answers are in the back of the book, and tutorial help and worked out solutions for the odd number exercises are at calcchat.com. So 7 or 9 or both. Do number 11, it has 2 parts. Do number 13, it has 2 parts. Do number 15, it has 2 parts. This one is both at CalcChat and CalcView, because it's in red letters. Do either 17 or 19. There are 2 parts to each of those. And again, 17 is, both of those are at CalcChat, 17 is at CalcView. Do either 21 or 23 or both. Do 25, it has 2 parts. Do 27, it has 2 parts. 29 has 2 parts. All the odds are at CalcChat, but 29's at CalcView. And either 31 or 33. Both of those are at CalcChat, but 33's at CalcView. Do 35, it has 2 parts. It's at both CalcChat and CalcView. Same for 37. Then do either 39 or 41, either 43 or 45, and we did 47A and 48A, but do either 47A or B and 49A or B. I think we did 49A, so do the B part. Finding arc length, number 51. That's at both CalcChat and CalcView. And then do 53, that's only at CalcChat, and 55 is only at CalcChat. Okay, do 57, it's at both. I really don't like 59 because they're giving you something that's wrong, but it's saying figure out what the error is. I hate for them to put down something wrong. They put big red X's to let you know it's wrong, but it's pretty simple to figure out what the error is there. Then 61 is a pretty interesting problem. A little bit different kind of a problem there. You have Dallas, Texas, and Omaha, Nebraska almost directly north-south over each other. So therefore, if you know the latitude of each of them, the difference of that is the angle, the difference in the latitudes. And then you can figure out what the distance is if you know the radius of the Earth, which they give you here. Okay, so that's 61. 63. I'd say for those, do any of the odds 61. Well, no, do 61, then any of the odds 63 through 69. So you don't have to do them all, but just pick some of those to do. And then the explorations are always, some of those are true-false. I hate true-false questions on tests, so I don't ever give them to you. But it is still is a good practice to think through and see what the answer is and why. But don't expect to see one like that on a test. And sometimes the writing might lead you to a paper topic. Usually I found that it doesn't, but you can look at those too. But you don't have to do any writing if you don't want to. So any questions? 4.1. Let's move on to 4.2. Okay, it's going to take me just a little bit to get 4.2 opened. PowerPoint is very slow. There we go. And we'll do slideshow from current slide. All right, still in Chapter 4, trigonometry, which, by the way, means measure. Metra is measure of triangles, basically. Except we're not going to even mess with the triangle yet. We're going to start with the unit circle, okay? We'll identify what a unit circle is and describe its relationship to real numbers. That's a strange way they say this, but I know what they're talking about, but it's still a strange way to say it. We'll evaluate trigonometric functions using the unit circle, and we'll use the domain and period to evaluate sine and cosine functions, and use a calculator to evaluate other trigonometric functions. So let's start with the unit circle. What would you think unit circle meant anyway? I think I may have asked this question before. What card game has a word that sounds a lot like unit? Uno. What does that mean? When you yell Uno? When you have one card left, it means one. So this is a circle of one. One what? What would you guess? Radius. The radius of one. That's what a unit circle is. Two historical perspectives, or hysterical, I don't know which, of trigonometry incorporate different methods for introducing trigonometric functions. When I was in school first learning, we did triangles first, and then we did unit circle and said, oh, that's how it works. Now they do unit circle first, and you're like, why? And then you do triangle and say, oh, I see now. Okay. So I don't know. They like to do unit circle. One such perspective follows and is based on the unit circle. So here's what's true about a circle of radius 1. Now, if you don't remember this from the past, here it is now. The general equation for a circle is x squared plus y squared equal r squared. That's a circle centered at the origin. Okay? And if that r is uno, 1, unit circle, that would then be 1. 1 squared would be 1. So x squared plus y squared is 1. What does that mean? That every xy point on the circle, every little pixel on that circle, if you did the x value and the y value, squared of each, and added them together, you're going to get 1. Every one of them. Now the obvious ones would be 1, 0. 1 squared plus 0 squared is 1. 0, 1. 1 squared plus 0. 0 squared plus 1 squared is 1. Negative 1, 0. Negative 1 squared is 1 plus 0 squared is 0. That would be 1. And 0 squared plus negative 1 squared, which is 1, would be 1. Yeah. So those are 4 obvious points on there. But every other point on that circle got to fit that equation. That's what it means to be on the unit circle. Okay? Those are the easy ones. All the rest of them are a little more involved. Okay? Now, here's the next imagination. Imagine wrapping the real number line around that circle. So here you have, let's have the real number line going straight up. Okay? Because here's our initial point, right? Initial side is the positive x-axis. So we start from here, and as you increase the angle here, you're going to take that real number line and wrap it around the circle, the unit circle. Okay? So when your t units up here, you're at some value xy here. Okay? Now this is for positive t's, going up this way. If your t was negative, you have it going downhill and wrap around this way. Well, guess what? Angles going clockwise are negative and going counterclockwise are positive. So you have the same sign convention here. This would be a negative. The t would have a negative value here, and that would be that. Okay? And you might think, why? What difference does this make? We don't worry about it. That's just the mindset here. Okay? Of the unit circle. As the real number line wraps around the unit circle, the real number t corresponds to every point xy on the circle. For example, let's go here, the point 1, 0, your t would be 0. Right? Okay? At 1, 0, it would be 0. Okay? Moreover, because the unit circle has a circumference of 2 pi, whoa, I thought that was the angle around. What is circumference? Formula for circumference. Second? Okay, it's 2 pi r, exactly. And what's your r? For the 1. Okay, so that's why it's 2 pi, because the radius is 1. Okay? It is the angle, but it's also the circumference. The real number 2 pi also corresponds to 1, 0, because this time you've gone all the way around, wrapped that thing all the way around till you got back here. Now your circumference is 2 pi. On the unit circle, the radius 1. So also that point corresponds to 2 pi. Okay? So, in general, each real number t also corresponds to the central angle theta in standard position, whose radian measure is t. Okay? So in other words, that length measurement of your arc length, that real number t that you're wrapping around the circle, corresponds to the central angle whose radian measure is t. Now we have been thinking of radian measure as some fractions of pi, which you can still think of that, but that's some real number t. So the angle is corresponding to t because the radius is 1. Okay. So with that interpretation of t, the arc length formula, S equal r theta, where theta is measured in radians. Okay? Since r is always 1, S is equal to theta. In other words, arc length of a unit circle is exactly equal to the angle. Same value. Remember, that doesn't have any units. The S usually does have a unit, inches, centimeters, whatever, but that came from the R, where R is equal to 1. So the S and the theta have the same values. That's what they talk about here. That T value that represented arc length also represents the angle. That's the advantage of the unit circle. You can talk about angle or arc length. Same number, just different units. So it indicates that the real number T, which is corresponding to S, is the directional length of the arc intercepted by any angle theta. So in other words, the T corresponds to every angle that you have. Every angle intercepts a point XY. That's what we're talking about. A lot of blah, 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 right? But it's true. Now, let's make sure. Yeah. So let's look at the trigonometric functions. From that preceding discussion, it follows that the coordinates x and y, remember, if you go t units around that circle, you're going to stop it at xy. A unique xy corresponding to that t. Okay? So that follows that the xy coordinates there are two functions of that real variable t. It's both the angle, measure of the angle and measure of the arc. You can use those coordinates to define 6 trigonometric functions of t. Okay? And here are the 6 trigonometric functions. I don't like the order they wrote them in. I like to refer to them as the sine function, the cosine function, the tangent function, the cotangent function, the secant function, and the cosecant function. Now, I know why they wrote them this way, but it seems just really bizarre to introduce it this way. They usually don't write these words out. They usually abbreviate them. Sine would be abbreviated SIN, cosine COS, tangent TAN, cotangent COT, secant SEC, that's not Southeastern Conference. Would cosecant be COS? No, because that's what cosine was. So we leave off the vowels and just do consonants, CSC. Okay, so cosecant would be CSC, cosine COS. Okay, so those are the 6 functions. We haven't told you what they were, but they are the 6 functions that relate the xy values to the t values. T being the angle measures. Okay? Now, here's how you do them. And they just sort of throw it on you to begin with. Later, I think it'll make a lot more sense. Well, I won't make it make sense now. I want you to notice something here. The x value here is right there. There's the x value. That drop a perpendicular from here, there's your x. Here's your y up here, right? What's your radius? 1. Right? It's a unit circle, right? Radius 1. Every radius 1. Okay. Now the sine of this angle theta, or of this value t, remember we can relate those because it's a unit circle, the sine of that t is going to be the opposite side, your y, over your hypotenuse, which is 1. So it's just going to be y. The cosine is your adjacent over 1, which is just your x value over 1. Your tangent is going to be y over x, okay? And we'll go from there. So they just plop it down here and say the sine of t is y. And you just have to take their word for it. But it's because it's the opposite over 1, y over 1. And cosine is the adjacent, which is x over 1, which is just x. Tangent is the ratio of the opposite over the adjacent, which is also the ratio of y to x, which is the ratio of sine to cosine. And here we start seeing the relationship between these 6 trig functions. Now, the cotangent is the reciprocal of the tangent. It's x over y. And the secant is the reciprocal of cosine. That's 1 over x. And the cosecant is the reciprocal of sine, which is 1 over y. So that, to me, is the way I think of these in that order. Go around the circle, okay? Whereas when they laid them out, they did this one, that, which I see where they got it, but it doesn't. Now, notice here we do have some problems, Houston, okay? Not with sine and cosine, because x is defined everywhere, y is defined everywhere, okay? But what we do have a problem with is the rest of these that have one of those in the denominator. Because there are places where y is equal to 0, like here and here, right? Y is 0 here, y is 0 here. Back one more slide or two. Yeah. Y is 0 here and here. So you can't have a y equals 0. Hang on to that. X is 0 here and here. So you can't have that ratio where x equals 0 there. So that's why they say over here, this is true everywhere except for x is 0. Where is x 0? At pi halves and 3 halves pi. And any 2 pi multiple of that. Okay? Y can't be 0 here because it's in the denominator. Where is y 0? It's 0 in pi. Okay? And then you repeat them here. Secant and tangent are somewhere there, and tangent and secant. So sine cos defined everywhere. The other 4 certain values that can't be defined everywhere else. Okay. Hang on to that thought for a few weeks into the term. We'll get back to that. Whoa! You don't tell me. We've run out of time. How did that happen? Okay. We'll pick up and go from there next time. I think we may have, let's see, did we get enough done to do any homework exercises? No, not yet. Let's just wait. Just focus on 4.1. You might be able to do the first few here, but let's do a little bit more and then we'll do it. Good deal. Any questions? Good. We'll see you then on Thursday and carry on. And by the way, I don't know if I said this or not, the WebAssign code is out there on Blackboard. I made an announcement and sent you an email. If you bought the new book with the thing, you can use it. I'm not going to make any assignments, so you don't have to go out and buy it unless you want to buy it. But it has a lot of good tutorials. It has a lot of examples and illustrations and interactive help. If you want to use it, use it. But if you don't want to buy it, you don't have to. I'm not going to make any assignments on it. It's just for your benefit. And when you buy a new book, you had to buy it. So, okay. Good deal. We'll see you Thursday. Bye-bye.